I froze, but luckily was able to save that. So we're back for the last 20 minutes of this lecture, whatever. So Lockheed, indirect effects. Indirect effects on Mount Lockheed, and we're not talking about aerosol indirect effects, we're just talking about not sort of like direct effects of the explosion itself, or the eruption itself, sorry. So the eruption itself actually was not an explosion, it was a basaltic eruption, which means that it was slow over many months. So that means that actually only 80% of the aerosols ended up in the stratosphere, and 20% were degassed directly from lava flows and remained really close to the ground. The aerosols that remained really close to the ground produced acid rains, strong acid rains that burned holes in leaves, killed trees, and irritated skin. It also emitted 8 million tons of fluorine, which over time settled into grasses and soils and killed a lot of grazing livestock. Overall, the famine that resulted from the eruption of Mount Lockheed due to this, not the climate changes, but due to the aerosols falling out onto sort of as acidic, killed over 10,000 people, which ended up being about a quarter of Iceland's entire population. From a climate perspective, the temperature in the northern hemisphere also decreased by about 1 degree Celsius. So compare this to Tambora, where the temperature across the entire globe decreased by about 1 degree Celsius. From Lockheed, the temperature just in the northern hemisphere decreased by about 1 degree Celsius. And so we can see in this figure here, right, the top graph shows the change in acidity per kilogram in the Greenland ice cap. So basically a measure of ash concentration in the ice on Greenland. So we can pick up a very strong signal from the eruption of Mount Lockheed in 1783. The bottom graph are the winter temperature records in the eastern United States, where there were extensive records being kept at this time. And you can see that after the eruption, winter temperatures did go down significantly and took many years actually to recover. So there was a decrease in temperature as a result of these aerosols being emitted up into the stratosphere. So where did those aerosols go? They went all over the northern hemisphere from Europe and China. It took about a month to get there. They ultimately triggered crop failures in Europe due to the acid rain, as I mentioned, and the decreasing temperatures. They really disrupted the food economy in Europe, which possibly was a major contributing factor to the unrest that led to the French Revolution in 1789. Benjamin Franklin also happened to be in Paris in 1783 to 1784. And Benjamin Franklin wrote about a dry fog, which greatly decreased the strength of the sun's rays, right? So he's observing these stratospheric aerosols decreasing the sunlight that's making it to Earth. And the way he figured this out actually is he couldn't ignite paper with a magnifying glass. The dry fog that was closer to the surface, right, the particulates that didn't quite make it up into the stratosphere were dense, creating like sort of this overcast cloud with low moisture, which irritated people's eyes and actually exacerbated asthma symptoms. And Benjamin Franklin actually was one of the first people to suggest that this effect, these things that he was observing, were linked to the volcanic eruption. So the first person to kind of say that volcanoes can influence the climate in really dramatic ways. Because remember, Lockheed happened several decades before Tambora. So Lockheed was a small basaltic eruption. It still had strong and deadly climate effects, and it was actually one of the first eruptions to reveal the effects that volcanoes can have on the climate. Okay, so we have these, sorry that I keep clicking ahead, and I'm sure that's like very confusing to people, but that's okay. I've decided it's okay. So these two case studies, and then we're going to talk next week about the third case study, which is Pinatubo. We're going to talk about Pinatubo in much more detail because we actually have a lot of observations from Pinatubo right? We have satellites, we have weather monitoring, we have data at the surface, because it happened in 1991. So we have a lot of data on that. So we're going to talk about that next week. But basically, these volcanic eruptions serve as good analogies for what might happen to the climate system if we were to actually go through with this stratospheric aerosol geoengineering. So, assuming that we do go through with it, we have to put a bunch of aerosols into the stratosphere. So how the hell are we going to get all these aerosols into the stratosphere? Because we can't just like erupt them out of a volcano. That's not how this works. So there are a lot of potential options that have been suggested. I hope by this point you've read the David Keith book, where David Keith is, of course, one of the first people to propose that we do this type of geoengineering. He's been a very strong advocate of geoengineering for many years on this specific type of geoengineering. And he talks about some of these methods in that book as well. So some proposals are we shoot it up there with artillery, I guess. We fly aircraft around the planet that are dumping aerosols out the back. Of course, those aircraft are going to be using fuel, so we have to offset the fuel as well. Maybe we let some balloons up into the stratosphere, and then they like emit aerosols like this, or maybe we blow the balloon up and it's like full of sulfur. Or maybe we just build a big tower and we send aerosols off the top of it. I don't know where or who or how or why. These are all considerations that we're going to talk about in extensive detail, hopefully in the Slack. Hopefully you have lots of sort of ideas and thoughts about this, and not just the science and the engineering, but also the ethics and the sociology and the politics of this, and the economics too. That said, there aren't a lot of studies that look at like whether this could work, right? Besides the volcano. So we have these volcanic eruptions, which provide an analogy. They're not exactly like a scientific study of whether stratospheric aerosol geoengineering will work. It's really hard to do a study in real life because you would have to put aerosols into the stratosphere. That comes with a lot of ethical and other questions. I do think David Keith, though, has been approved for doing one of these. So I'm not sure what will come of that. But most of the studies that have been done have been computer model simulations. So we've talked a lot about, or we talked a bit about how we use computer models to model the climate, computer simulations. So here are the examples of here's the results of one example study where they actually did this. They tested what would happen in a climate model if we were to put a bunch of aerosols into the stratosphere. So this figure here shows the June, July, August temperature difference from now if we were to A, double the amount of carbon dioxide in the atmosphere, and then B, double the amount of carbon dioxide in the atmosphere and emit 2 teragrams of sulfur per year into the stratosphere. Teragrams are a lot. 2 teragrams is a lot of fucking sulfur. And we're going to talk in extensive detail. We're going to have a whole math in-class exercise that we're hopefully going to do in groups in the Slack in next week about exactly how much aerosol we need to put in the stratosphere. And it's a lot. 2 teragrams is a lot of aerosol of sulfur. So doubling CO2, if you remember, we talked about how much CO2 there is currently in the atmosphere in parts per million. And this is the point in the class where I would ask you how much carbon dioxide is in the atmosphere in parts per million, and you're all brilliant, and you would say 410 parts per million, which means that for every 1 million air molecules, 410 or so of them are carbon dioxide. So if we were to double that, 820 parts per million of carbon dioxide, we would get the graph on the left. We would get global temperatures increasing anywhere from 1, 2, 3, 4 degrees Celsius of warming. This is about in line with what we expect from some of the sort of middle-of-the-road climate modeling climate warming simulations. The graph on the right shows the same thing, but then also we're putting in these aerosols into the stratosphere. And you can see that actually, if we do that, the temperature of the globe only goes up by between 0, and in some cases actually goes down a little, between 0 and maybe 1 or 2 degrees of warming at the most. So cutting down the amount of warming really significantly, at least in this model simulation. So the moral of the story is that at least in the model simulation, it works. Here's another way to look at it. So here again are the June, July, August differences with and without the 2 teragrams of sulfur in the stratosphere. So the top plot is a cross-section of the aerosol concentration by latitude. So here's the equator, this is the South Pole, this is the North Pole. You can see, and then kilometers, right? So 0, 10, 20, 30, 40 kilometers above the surface. You can see that those aerosols are getting and staying in the stratosphere. They're getting up to 10, 20 kilometers above the surface, and they're staying there, right in the stratosphere. Well mixed. If we look at the whole globe, where do they go across the globe? This is the concentration of aerosols across the globe, the distribution. You can see that the highest concentrations are at the equator, and then the North and the South Pole. That's due to circulation effects and the way that air moves around the planet. And then finally, if we just look at the model temperature response, not looking at the doubling of carbon dioxide, none of that, just what effect do these aerosols have on the climate standalone without anything else? And you can see that they decrease, these are all negative numbers here, they decrease the temperature of the planet between 1 and 4 or 5, in some cases, degrees Celsius. So pretty significant decrease. So the moral of the story is that at least in a model, at least in a climate model, this idea of putting aerosols into the stratosphere to reflect sunlight does, in fact, work. What are the ethics of that? What are the politics of that? What are the engineering questions with that? That's something that we are absolutely going to discuss. So write all your questions down, write all your thoughts, your comments down, and I really want to have this conversation when we meet again. All right. What are some other possibilities that we could do to increase the albedo of the planet, reflect sunlight, cool the temperature of the planet, enough to offset the global warming? So now we're getting into a little more sci-fi stuff, but we could put a mirror in between the sun and the earth. We could put one big giant mirror, or we could put thousands of tiny mirrors. Either way, they need to add up to, or be, if it's just one mirror, 600,000 square miles, which is about the size of Greenland. So that's a big mirror that we somehow have to, I guess, build in space in between the Earth and the sun to reflect, and that's not even reflecting 2%, right? Because we said in the beginning we need to reflect maybe 2% of sunlight. That only reflects 1% to stabilize the climate a little bit. So that seems very realistic thing that we could do. Not to mention, we would have to put that mirror or those mirrors at the Lagrange point, L1. So there are several Lagrange points in Earth's orbit around the sun. There's Lagrange point L1, L2, 3, 4, and 5. So you can see Lagrange point L1 is out here past the moon, closer to the sun than the moon. It's stationary, which means it wouldn't really orbit. It would just kind of be fixed with the Earth, so it would be at the same point all the time. It would be gravitationally stable. There are other options that we could do. For example, we could put these mirrors in between the moon and the Earth in an equatorial orbiting path where some of our climate monitoring satellites are, for example. But this seems like it would be, as if the whole thing wasn't expensive enough, this seems like it would be prohibitively expensive, that it wouldn't even be a consideration from serious people. All right. Another thing that we could do, and I'm really sad that we have to do these lectures remotely because I was really excited about this part in particular because of all of the architects that are in this class this semester, and I was really interested in like your insight on this and like what y'all think about this. But we could paint all of the roofs in all of the world white, and all of the pavement too if we wanted. We could do that. That would definitely increase how bright the surface of the planet is, and it would reflect more sunlight. There are, of course, many advantages and disadvantages to this, and there are even more than this. But these are just some that I found. So obviously the advantage is that these would reflect solar radiation. And if done properly, if engineered properly and designed correctly, could lower the temperature of the planet a little bit to offset some of the warming from climate change. But unless the nearby buildings and nearby structures were fitted with reflective glass or other types of mitigation, the solar radiation that gets reflected off the pavement or the roofs would actually increase the temperature in those buildings, would increase the demand for air conditioning, increase the demand for energy usage, and this would probably increase the amount of fossil fuels that we use and increase the global temperature. So although they could decrease the temperature in a particular building, or even mitigate some of the heat island effect, and possibly lower temperatures globally worldwide, they may actually also increase global temperature, and more work needs to be done on which way which weather would warm or cool. And I'm really actually curious for some of you who are more in this related to this field, architects for example, on what your thoughts on this are and what some research that you found says. So what I found, some papers that I found say that this technique could maybe give between 0.01 and 0.19 watts per meter squared of globally average negative forcing, so about 0.2 watts per meter squared, right? That's just a measure of the radiation, the increase in radiation that would be reflected away. This is pretty small relative to the 3.7 watts per meter squared of positive forcing from a doubling of carbon dioxide. Now, we could just paint more than just roofs white. We could paint lots of white things white so that we end up covering 1% of the land surface. Remember, 1% is how much we need to increase the reflectivity. So let's say we cover 1% of the land surface, 10 to the 12 square meters, 10 trillion square meters. This would cost like $300 billion per year, which would make this, from a cost-benefit analysis, one of the least effective but most expensive methods that we consider here in this particular lecture. So I'm not particularly sold on white roofs. They could have smaller scale advantages, especially like within cities, that have a lot of air pollution or are particularly warm under the urban heat island effect, but I'm not sure about a global reduction in climate change. But I am very curious to have this conversation with you all. So collect your thoughts on the white roofs thing. Okay, something else that we could do is we could brighten marine clouds. I mentioned in the beginning that aerosols, if they get ingested into clouds, can actually make those clouds brighter, and that brightness, right, would ultimately reflect more sunlight. And so this would work, in theory, to cool the planet, to offset some of the warming from climate change. But it's not clear exactly how we would do this and where and what mechanisms we would use. We do have some analogies. We do have marine cloud brightening happening even now. A lot of ships that cross the ocean, specifically the Pacific Ocean. I'm from Southern California. We have a lot of ships that come in and out of the port of LA, travel to, for example, East Asia. And as they pass under cloudy skies, the emission of aerosols from their smokestacks actually does get into the clouds and does brighten the clouds. And we have evidence of this from satellites. Here's a satellite image showing those ship tracks. So these lines are all a ship traveling under these clouds, emitting aerosols. Those aerosols are getting into the cloud, and what they do actually is they decrease the size of the cloud droplets. And the smaller the cloud droplet size, the more the cloud is able to reflect, the brighter the cloud appears. And so we actually see lots of ship tracks every day. And so there are studies that you know, look at the effect that the effects that these ship tracks have on temperatures, on climate, and we are going to talk about all of that in more detail after the Pinatubo lecture. When we kind of pull all this together, we're going to talk about all of the sort of scientific and, as I mentioned, ethical and political or whatever questions about these methods. And so we'll talk about some of those studies then. How we would do this is another important question. So one thought is that we have a ship with a bunch of smokestacks. That ship would have to run from solar power or wind power, some sort of non-fossil fuel power. Otherwise, like, what's the point, right? We're trying to offset climate change. So solar power, I guess, or wind power, or wave power, and then it's kind of traveling across the ocean. Maybe it's automatic, or there's like someone living on it. I don't know. And it's just like pumping aerosols out of its smokestacks. Those aerosols are getting into the clouds. They're brightening the clouds, and then they're cooling the climate. What are the negative effects of this? What are the advantages? What are the disadvantages of this? What do some people say about this? To be continued in 2 lectures. Okay, instead of putting a mirror or aerosols, we could just put sunglasses over the Earth. So we could put a sunshade, a Fresnel lens. We would also have to put this sunshade at the Lagrange L1 point, so way out there past the moon. This wouldn't reflect necessarily sunlight, it would refract sunlight. So it would refract sunlight, they're kind of like sunglasses, right? The only problem is that it would need to be about 1,000 kilometers in diameter, which in terms of miles is feet. I don't know. It's too hard of a I don't know. I'll just leave it up to the people who can do this conversion better than I know there's a few of you in this class who can do this conversion better than I can. But 1,000 kilometers is a lot. It's far, many miles. But it would have to be a few millimeters thick. So 1,000 kilometers in diameter and a few millimeters thick. So that seems realistic. And then finally, some other propositions which we'll talk about, but not too much because they're very far-fetched. We could enhance the sulfur cycle of the ocean. I'm not convinced that we could even actually do that, and then I'm not convinced that that would actually have a more reflective effect. We could dump a bunch of reflective garbage in the ocean. I don't know why we would want to do that. Or we could blow up like side of the moon, and that would put dust in space orbiting the Earth rather than in the stratosphere, but have a similar effect to sort of stratospheric aerosols, the moon dust. Okay, so that is now officially, finally, the real end of this lecture. I feel really weird talking to you all through a computer, so I hope this isn't super weird, and send me lots of like notes of encouragement that make me want to do the rest of these. But I hope you got a lot out of this. You get to watch it now. The benefit is that you get to watch it like 1,000,000 times if you want and see my amazing lecturing skills. But come prepared to our Slack discussion, which I will be sending out notifications for how that's going to happen very soon. So, okay, cool. Thanks. See you. Bye. How do I stop recording?